In section 9.3, we're going to look at the topic of finding the area bounded between two curves. So what I've done here is drawn a picture of a certain situation where we have two functions. The upper function is indicated by y equals f of x, and the bottom function is indicated by y equals g of x. And then I've also marked off an interval from x equals a to x equals b. You can see that what I've created is a region which I've shaded in here in red. That is the area of the region that we're looking for. So this is just an extension of what we learned in the first section of chapter 9, which was the area under a curve and above the x-axis. This time we're not going to limit ourselves to the x-axis. We're going to have a lower function called g of x. So the theorem states that if you have two functions, f of x and g of x, and they're both continuous function on some closed interval a to b. So both functions have to be continuous, and those functions are enclosed by an interval a to b. If one function, f of x, is always greater than the other function, g of x, for every value of x in the interval, then the area of the region formed by the vertical lines x equals a and x equals b, as well as the two functions, is given by the following definite interval. So all we do is we evaluate the integral from a to b, the first limit and the second limit, and then we just subtract the two functions. We take the upper function, f of x, and we subtract the lower function, g of x. This will give us a brand new function, which we're going to integrate, and then we're going to evaluate between the values of a and b. The thing I want to stress, though, is that in order for this to work, the function f of x has to be always above the function g of x. If at some point the functions cross, then that's a different situation. So it has to be as shown in this diagram right here. So now we'll do an example. In this example, we're being asked to find the area bounded by the function f of x equals x squared minus 2x plus 3. Now that's a quadratic function, has a y-intercept of 3, and is opening up. So I've drawn a sketch of what that function would approximately look like. The function g of x, which is negative 1 subtract x squared, that's also a quadratic function with a negative leading coefficient, so it's opening downward and has a y-intercept of negative 1. So I've drawn, again, a rough sketch of what that parabola would look like. And the vertical lines, x equals negative 1 and x equals 2. So what I've done here is drawn a region. The region is below this function f of x, above the function g of x, and in between the interval negative 1 and positive 2. So we want to find the region that I've shaded here with green. So according to the theorem we just learned, the area that we're looking for, a, is going to be the definite integral between negative 1 and 2. And then inside the integral, you always take your upper function and subtract your lower function. So this is going to be x squared minus 2x plus 3 subtract negative 1 subtract x squared. And of course, we're integrating that with respect to x. Now, before we find the actual integral, we're going to want to simplify the integrand, the part that's inside the integral sign. So this is going to be the integral from negative 1 to 2. Now, if we distribute this negative through the bracket, this is going to become a positive 1, and this is going to become a positive x squared. So collecting all my like terms, I'm going to have an x squared plus another x squared. So I'm going to have 2x squareds. I'm going to have a minus 2x, and there aren't any x's in this function, so we're just going to have minus 2x. And then we're going to have plus 3 plus 1. This is going to be a plus 1. And so we have plus 4. And we want to integrate all of that with respect to x. So using our power rule of integration, we're going to add 1 to the exponent and divide. So this is going to be 2/3 x cubed. Subtract. We're going to add 1 to the exponent, which will make that x squared, and then divide by 2. So this will just be x squared, and then plus 4x because of the constant 4. And we're going to evaluate that integral between -1 and 2. I've suggested all along that when you evaluate a definite integral, instead of writing the whole thing out as a long expression, it's much easier to avoid mistakes if we treat each one separately. So we're going to find capital F being our antiderivative, at 2. So we're going to plug 2 into our antiderivative. So we're going to have 2/3 times 2 cubed minus 2 squared plus 4 times 2. This is going to be 8/3. This is going to be 8 times 2/3, which is 16/3 minus 4 plus 8. And if we get a common denominator of thirds here, this is going to work out to be 28/3. If we then evaluate the antiderivative capital F at -1, we're going to get 2/3 times -1 cubed, subtract -1 squared, plus 4 times -1. -1 cubed is -1, so this will be -2/3. -1 squared is +1, but we're subtracting it. And then minus 4, and that works out to be -17/3. So that the area that we want is going to be f at 2 minus f at 1. It's going to be the definite integral that we're evaluating here, which would be 28/3 subtract -17/3, which works out to be 45/3, which is 15 units squared. So using this theorem, we're able to now expand our ability to find areas to more than just a function and a horizontal line, but now the area between two functions. We're going to finish off this section by discussing a possibility that may arise, and that is, what if you have two functions, which I've indicated by g of x for the blue one and f of x for the red one? What if over the interval that you're trying to find the area of, what if the functions change position? Originally, the red function f of x was above the blue function, and then at some point they're going to cross. At some point right here, we'll call that x equals c. The two functions intersect, and then the red function f of x becomes the lower boundary. Well, the theorem that we just looked at said that the function always has to be above the lower one in order to find the definite integral. So what you would do in a situation like this is you'd have to split the question up into two parts. You'd first of all have to find the area, we'll call this area 1, just this region right here. In that region, the function f of x is the upper function and the function g of x is the lower function. So the area for 1 would be the definite integral from a, the original endpoint, to c, and it would be f of x minus g of x with respect to x. But at the moment that the functions cross, we would now have to switch, and we would have to say that g of x is the upper function. So this region right here, which I'll call A2, A2 would be the definite integral from c to b. And now we would have to take g of x is our upper function and subtract f of x with respect to x. And as a result, our overall area that we're looking for, which is the entire area, is going to be the area of 1 plus the area of 2, which would be the integral from a to c of f of x minus g of x dx plus the integral from c to b of g of x minus f of x. So it is possible to find areas of regions if the functions cross. You just have to treat them as separate regions. And obviously this could happen multiple times. The graphs could cross, and in each case you'd have to determine the intersection point and find the area of each individual region.